Let's say the eigenvector trick behind Google search as we continue with the mathematics of artificial intelligence. Right. So the eigenvector trick behind Google search. So Google search, of course, has been with us for a very long time, even before we now have AI that has taken over the discussion about computing. So from eigenvectors to PageRank, that's what we are looking at. And we see the applied AI mathematics that the web contains billions of interconnected pages. Now, the question is, how can a search engine decide which pages are important? By the way, there are many other search engines apart from Google, but Google seems to have, to have outsmarted, should I say, or it's more the most popular of the search engines we know, I think. So one of the most beautiful answers comes from linear algebra. A web page can be important because other important web pages point to it. So it's more like you have all kinds of web pages, but then other web pages point to the more the other web pages point to a particular web page, the more important that web page is. So this idea leads to PageRank, one of the most famous applications of eigenvectors, matrices, graphs, and probability. So the mathematical pipeline is something like this. You have a web, then you form a graph of webs, then you have a matrix formed from that based on how one website points to the other, and then you can compute the eigenvector, which leads to page rank. So the learning objectives here include the following. By the end of this lesson, you should be able to explain what an eigenvector is. I mean, I've done several playlists that where eigenvector has come up. The very first playlist I did on this channel was on matrices, and so there, of course, at some point we get to talk about eigenvalues and eigenvectors. Then, of course, talking about numerical analysis, there we had to talk about numerical analysis as it relates to partial differential equations and things like that. There we had to talk about eigenvectors and eigenvalues. Of course, also talking about differential equations, we had to talk about eigenvalues and eigenvectors. Even under linear algebra, so under many circumstances, we have to talk about eigenvalues and eigenvectors. So then, of course, another thing we want to be able to do is to represent web pages as a directed graph. I have a playlist on network and graph and network theory. So there you understand the idea of a directed graph and undirected graph. Then construct a transition matrix from hyperlinks. Then explain the mathematical idea behind PageRank, derive the PageRank equations for a small network, explain why PageRank is an eigenvector problem, understand the random cipher interpretation of PageRank, explain the damping factor and teleportation, then implement PageRank using Python, understand the power iteration method, explain why PageRank is useful for ranking network nodes, and of course, connect PageRank to broader applications of linear algebra in artificial intelligence. So that takes us to the big idea about um, the eigenvector vector trick behind Google search. So one of the most important ideas behind PageRank is surprisingly simple, and it is this that a web page is important if important web pages link to it. So a web page is important if important web pages link to it. So imagine a scenario of human networks. Like imagine you go for a party, and then you meet 10 people, and of these 10 people, nine of them keep telling you that a particular person is their mentor. So out of 10 people, nine people told you a particular person is their mentor. So that tells you how important that mentor is, right? So it's the same idea that a web page is important if important web pages link to it. So this creates a secular definition. If you want to know whether page A is important, we need to know which pages link to A. So, but to know whether those links are valuable, we need to know how important the linking pages are also. So if important people say a particular person is their mentor, it means that person is really important too, right? Therefore, importance of A means importance of pages linking to A. So, but importance of linking pages also implies importance of pages linking to them. All right. So the problem is recursive now. So a page is important if it points to if many pages point to it, and how important those pages pointing to it are, that's how important it is. So, and of course, because it is important on its own, if it also points to other pages, it means that those pages are also important. So importance of linking pages implies importance of pages linking to them. So The problem is recursive. PageRank turns this recursive problem into a problem in linear algebra. So this simple concept of websites, sites referring to other sites and other sites referring to them or something like that can then be modeled as a matrix problem, as a linear algebra problem involving matrices. So let's talk about the idea of an eigenvector. Suppose we have a matrix A and a vector X. Of course, it's usually a square matrix. Normally, multiplying a matrix by a vector changes the vector. So if you have matrix A multiplied by a vector, you get a new vector. So an eigenvector is special because multiplying it by the matrix does not change its direction. So that's where the idea of eigenvector comes from. So instead of having the direction changed, we have a. So when you multiply a matrix A by a vector X, it becomes the eigenvalue multiplied by the vector X. So A is the matrix, X is an eigenvector, and lambda is the corresponding eigenvalue. So the eigenvector keeps the same direction. So it's more like we talk about vectors, we talk about what's this now? Vectors and scalars. Yeah, we talk about scalars and vectors. So eigenvalues are scalar quantities, while eigenvectors are vectors. Of course, even the name gives it away as a vector. So the eigenvector keeps the same direction, while the eigenvalue tells us how much it is, how much it is stretched or compressed. So eigenvector is about direction. Eigenvalue talks about stretching or compression. Therefore, AX is equal to lambda X is the fundamental eigenvector equation. So this is the eigenvector equation. So a simple eigenvector example then becomes this. If you consider matrix A, which is 2003, if you take the vector x1, which is 10, then AX1 will be 2003 multiplied by 10. Of course, that simply means you multiply 2 by 1, you get 2, multiply 3 by 0, you get 0. You can write 10 twice, and then you put 20 by the first one. You get 1 times 2, 2, 0 times 0, 0. So 2 plus 0 is 2. Then this other one, 1003. So 2 times 1 plus 0 times 0, that's 2. Then 0 times 1, 0, 3 times 0, 0. So this can then be written as this now. It can be written as AX1 equals 20, which is 2 into 10. So this 2 now serves as the eigenvalue. So, and if 2 is the eigenvalue, then we can say x1. So we can then have ax1. So x1 now is the vector itself, as you can see from the beginning here. So we come back to that x1. Similarly, we can say that x2 is 0, 1. So which satisfies that ax2 is equal to 3x2. Therefore, x2 is another eigenvector with eigenvalue 3. So this x2 now can actually serve as another eigenvector with eigenvalue 3, like that. So, and that, of course, is attached to, yeah, I mean, so we have that. So question is, why do eigenvectors matter? So eigenvectors appear throughout applied mathematics, as we see it in data, and also in data science and artificial intelligence. Examples include in PageRank, which we're talking about right here. So PageRank, ranking web pages, eigenvalues, eigenvectors come up there. Then PCA, that's principal component analysis, for finding important directions of variation. So if you have you're working in many dimensions, right? And you want to just distill everything down to what matters most. So you can do something like principal component analysis. So, and eigenvectors help with that. Then you have spectral clustering. So that helps to find structures in networks. So eigenvectors help us to find structure in networks. The Markov chains, eigenvectors help us to find stationary distributions. Then graph analysis, eigenvectors help to undertake network structure. And in dynamical systems, eigenvectors rather, help us to understand long-term behavior. I mean, we've been talking about eigenvectors all along. So the important lesson is that the same mathematical object can solve very different real-world problems depending on the context. So for PageRank, the eigenvector represents a stable distribution of importance across a network. So in PageRank, eigenvector represents a stable distribution of importance across a network. So let's talk about representing the web as a graph. A web page can be represented as a node. So a hyperlink can be represented as a directed graph. So so a web page is a point that can be pointed at. So for example, A is directed towards B, means that web page A contains a link to web B. So a small web can therefore be represented this way. So here you have this simple one. So A points to B, A is linked to B, A is linked to C, B, then uh B is linked to C, like that. So you can see B is not linked to A. So A is linked to B and C, and B is only linked to C. But A is not linked to B is not linked to A. So the direction matters. The link A to B does not automatically mean that is linked to A. Therefore, the web naturally forms a directed graph. So a directed graph is a graph where you have an arrow pointing in a specific direction. Then you have why counting links is not enough. So since we know that a page is important if other web pages point to it. So it's not just enough to just count the web pages pointing to a particular web page. So why counting links is not enough then. Suppose page A has 100 incoming links and page B has 10 incoming links. A simple link counting method would conclude that A is more important. But consider the source of those links. Suppose all 100 links of A come from obscure pages, maybe pages that are not really so important. Meanwhile, all 10 links to B come from extremely important pages. So the 10 links could potentially be more valuable than the 100 links. So it's more about quality over quantity. Therefore, not all links are equally valuable. So a link from an important page should contribute more importance than a link from an unimportant page. This leads to the central page rank idea that a page receives importance from the pages that link to it. So it means you're as important as people that know you. Of course, you may know, of course, you know some people that don't even know you. So it means you are as important as the people that know you. But the amount of importance transferred depends on the importance of the linking page. So let's talk about the page rank principle now. Let Ri represent the importance of web page I. So we're talking about importance here. So let it be the importance of page I. So a simplified page rank equation is simply this, that the importance of a web page I is equal to the summation from J to I of the importance of J all over L of J. So Ri is the page rank of page I, Rj is the page rank of page J, and then Lj is the number of outgoing links from J. Number of outgoing links from J. So this J pointing to I now. So the term Rj over Lj represent the amount of importance that page J passes, that page J passes through each outgoing link. Therefore, a page receives importance from the pages linking to it, and important pages contribute more importance. So, for example, let's look at a three-page web. Consider three web pages ABC with links A to B, A to C, B to C, and C to A. So A is linked to B, A is linked to C, then B is linked to C, and then C is linked to A. So the network can be visualized simply this way. You have A is linked to B, A is linked to C, and then C is linked to A, and B is also linked to C. So of course, this is not the only way you can do it. You can do it in whatever way, as far as the arrows point correctly. So you can even have like a triangle, where you have so A something like this, A B A C B C C A, right? A B A C B C C A. So you have A B C. So A B A C B C and then C A. So you can have it okay, and then C A. This one now. So you can also do it this way, like I said. So that is equally okay. So the number of outgoing links is this. So outgoing links from A now. So how many links are going out of A? So from A, you have link going to B and C. So the number of outgoing links is 2. Then from B, how many links are going out of B? Only one. The link going to C, that's 1. Then outgoing links from C. Only one link is going out of C, going to A. Then we can let the page rank scores be. So if the page rank scores are RA, RB, and RC, so that's the rank for A, the rank for B, the rank for C. What does that tell us? We can then derive the page rank equations as follows. Imagine that page A receives a link from only C. So page A receives a link from only C, as you see there. Therefore, we can say that the rank of A is equal to the rank of C. So page B receives a link from A also. So since A has 2 outgoing links, it passes half of its importance to B, right? So the RB now will be, since A has 2 outgoing links, so it means A is sharing its resources to 2 links, to 2 pages. So that means that the rank of B now will be the importance of A divided by 2. the rank of A divided by 2. And page C receives links from both A and B. In that case, because page B receives links from both A and B, then the rank of C will be half of A. A is sharing to two other pages, so it receives half of the rank of A. And then since uh, C receives link exclusively from B, then as you can see, C receives X only from B. Okay, B only sends to C. I think it's about the sending, right? About the outgoing. So B only gives to C. So it gets all the attention of B. So you have RB. So the complete system then is this. RA, the rank of A is equal to the rank of C, and the rank of B is half of the rank of A, and the rank of C is half of the rank of A plus the rank of B. Notice that the importance of one page depends on the importance of other pages. So a page that is as important as the pages linking to it. So this is the recursive nature of PageRank. So this is here we derive the PageRank equations that way. Now, solving a three-page example, imagine from RB equals RA over 2 that we have up there. So if we can then obtain that RB is equal to 0.5 RA. So the rank of B is half of the rank of A. So from RA equals RC, then we know that we can obtain that RC is equal to RA also. And therefore, we can say that the ratio of RA to RB to RC is equal to 1 ratio 0.5 ratio 1. So if you want to take away the fraction, that's like multiply through by 2. That's 212, if you like, 212. So it means that page A is twice as valuable as page B, and page C is also twice as valuable as page B, like that. So the page rank values must sum to 1. So since the page rank values must sum to 1, then it means that RA plus RB plus RC should be equal to 1. And if you substitute the relationships, we know already that RA, so we have RA, right? Then RB is 0.5 RA and RC is also RA. So in all, we have 1.5. This is 1 plus 1, 2. That's 2.5 RA equals 1. So that means that the rank of A is 0.4. And if the rank of A is 0.4, we know that RB is half of RA, which is 0.2. And automatically RC is RA, that's 0.4. Therefore, we can say that page A is ranked 0.4, page B is ranked 0.2, page C is ranked 0.4. So pages A and C have equal importance, while B has lower importance. So while B has lower importance, that's simply what that teaches us. So that's what that teaches us, that page A and C have equal importance while B has lower importance. Then turning the web into a matrix now. So now we express the same problem using linear algebra. Define the page rank vector R to be RA, RB, RC, and we construct a transition matrix M. Each column represents how the importance of one page is distributed among its outgoing links. So page A distributes its importance equally between B and C. Page B sends all its importance to C. Page C sends all its importance to C. Therefore, what that tells us is this. Therefore, so for M now, so you have A, B, C, A, B, C. So A to A, nothing, 0. A to B, A sends to B and C. So this is A, B, C. So A only sends to C. So this gets all the 1. Then B here. So B sends to A, half. Then B does not send to B or C. Then B sends to then C sends to A, C sends to A, it has sent to, okay, A sends to both B and C, so we can just write half half here. Then C sends all its importance to A, and that is 1 right here. So the page rank equation then becomes like that eigenvector idea. So we can say this is MR equals R now. So MR is equal to R. So the eigenvector trick that we have then is this. We have MR equals R. So, but we can rewrite this as MR equals 1R. Compare this with the definition of an eigenvector. The matrix A multiplied by the multiplied by a vector X. That's like MR. And then this one here is like the eigenvalue and then the X again. Therefore, we can say that A is equal to M. That is, the M you have here is your matrix A, and X is equal to R, the R, and then lambda is equal to 1 here. So Hence, R is an eigenvector of M. So R is the eigenvector we are looking for, corresponding to the eigenvalue lambda equals 1. So this is the central mathematical trick behind PageRank. So that's the core of what we are dealing with. So computing the eigenvector with Python now. So import numpy as NP. So you have the eigenvectors. This is based on this transition matrix we have here, like this. So we compute the eigenvector with Python, import number as NP, and we declare the matrix as an array. So it's a list of lists. It's a list of lists, right? And then no, it's a so we form the array using the lists for each row. So we can have eigenvalues and eigenvalues and eigenvectors equals from NumPy, we have a module called linear algebra, and from that module we have a function called Eig. That's for eigenvalues and eigenvectors of this matrix. So if we do that, we get that the eigenvalues are 1 plus 0 point j. That's simply 1, right? So 1 is an eigenvalue like we saw before. Then you also have another eigenvalue 0 minus 0 0.5, another minus 0 0.5, like that. Of course, you have the complex parts like that. So to now extract the PageRank vector, so we find the eigenvalue closest to 1. So the eigenvalue closest to 1 is actually this one right here. So we index np.agmin, so of the absolute value of all the eigenvalues minus 1. So we extract the corresponding eigenvector. R is np.real. So we are interested only in the real parts. So R is np.real. Eigenvectors we index. Then we make entries positive. So R is np.absolute value of R. So we normalize so that the scores sum to 1. So in that case, now R is equal to R over R dot sum. And then, so this normalization here. So at the end of the day, we have 0 0.4, 0 0.2, 0 0.4, like we had before. Okay. So we have that. So this is the procedure to deal with that. Don't forget, we got eigenvalues here already. So the eigenvalues we got here, they are the ones we invited here, and same for eigenvectors. So with that in place, we can then interpret the Python result. The Python calculation should give approximately 0 0.4. I mean, that's what we got for sure. Therefore, R is 0 0.4, 0 0.2, 0 0.4. The eigenvector has recovered the same PageRank values that we obtained manually. So this demonstrates an important principle. A recursive ranking problem can be transformed into an eigenvector problem, like that. So problems with the simple PageRank model. Our simple model assumes that every page has outgoing links. So the real web is much messier. So not every page has an outgoing link. So two important problems arise now. We can have some dangling pages. A dangling page is a page with no outgoing link. So it's dangling. For example, is linked to B is linked to C is linked to D, and there's no way back. So if D has no outgoing links, D has no outgoing links, its page rank has nowhere to go. So another problem we have with a simple PageRank model is the idea of disconnected components. So imagine A goes to B and B goes to A, C goes to D, and then D goes to C. So there's no connection between the two groups now. So you have A, B, C, D, and there's no connection of any, so there's no flow from B to C or A to D and all that. So a random surfer starting in the first group can never reach the second group. So if you are in the loop of A to B, you can never reach the loop of C and D. And that's what I think, that's where the idea of things like echo chambers come from. So you're only in that web, you don't know anything outside the web you are in. So these problems motivate the idea of teleportation. So disconnected components leads to the idea of teleportation. So let's look at the random surfer model. Imagine a person browsing the web. At each web page, the person has two possibilities. Option one, you can follow a hyperlink with probability D, and the surfer follows one of the page's outgoing links. Then option two is to teleport, and teleportation is with probability D, with probability 1 minus D, right? So it's either you follow a hyperlink or you teleport. So with probability 1 minus D, the surfer jumps to another web page without following a hyperlink. So the parameter D is called the damping factor. A commonly used conceptual value is D equals 0.85. So the random surfer interpretation gives PageRank a probabilistic meaning. So PageRank becomes the long-run probability that the surfer is visiting each web page. So let's see the damped PageRank equation. With teleportation, the PageRank equation then becomes R. Before it was just MR equals R straight up. But that because that's too simple, because not every web page is linked to another web page, and that leads us to the idea of either following the hyperlink or teleporting. So, of course, if a page does not have any hyperlink, you are left with no chance than to teleport, and that leads to this idea now. So R is equal to, so for a website that has a hyperlink, so um we have D times MR. So this is still the MR equals R, right? But we now have a factor D, a damping factor D now, that talks about the possibility of following a hyperlink. But if there's no hyperlink, then we have teleportation happening. So R is the page rank vector like we know before, M is the transition matrix, D is the damping factor like we know, and V is the teleportation distribution. So for uniform teleportation across n pages, then we have that V is equal to 1 over n into 1, 1, 1, 1, like that. Therefore, we can say that R is equal to, so if you have uniform teleportation, if you have n pages now, if you're restricted to a certain number of pages, so instead of just having 1 minus d multiplied by v, so it now becomes 1 minus d over n multiplied by 1. So this is the fundamental page rank equation used in our simplified mathematical model. So why is teleportation important then? Teleportation prevents the random software from becoming permanently trapped. Okay, if not for teleportation, there will always be echo chambers and all that. So it helps deal with dangling nodes. Dangling nodes are nodes that are, nodes that don't have any hyperlinks. Then you have disconnected components. It helps disconnected components. So where you have clusters of pages that without any possible bridge to other pages, then you can have cycles. So just moving around in the same cycle. Then you have poorly connected regions of the graph. So without teleportation, we have R equals NR. With teleportation, we have R equals DMR plus 1 minus DV. So the software can therefore escape any region of the network. So teleportation makes it possible to escape, to leave a particular network, even if some of the pages don't have hyperlinks, because the software can then go to any random page. So this makes the ranking much more stable in this case. So the important intuition is this: the software usually follows links, but occasionally jumps somewhere else. So that's the idea. So example with damping now. So return to the three-page network that we had before, where the transition matrix was 0, 0, 1, half 0, 0, half 1, 0. And then we have we let D be 0.85, the damping factor is 0.85. So that's the probability of following a hyperlink is 0.85. So there are three web pages. So under uniform teleportation, so if you have uniform teleportation for uniform three web pages, right? So the page rank equation then becomes R equals 0.85 times MR plus 0.15. That's 1 minus 0.85. That's 0.15 times V, which is 1 over 3, 1 over 3, 1 over 3. So each page, therefore, receives a teleportation contribution of 0.15 over 3 in this case now. So because, this 0.15 over, if you take the 1 over 3 out now, it divides this. So each page therefore receives a teleportation contribution of 0.05. So damped equations for the three-page network then. So for page A, so the page A we dealt with the other time. So RA is equal to 0.85 RC plus 0.05. Then page B, RB is 0.85 RA over 2. So we just impute all these things like they were before. So the only factor now is that we now have D and 1 minus D, and this is 0.05. So for page C, we have RC 0.85 into RA over 2 plus RB plus 0.05. Together, then, we have RA to be 0.85 RC plus 0.05, RB 0.35 RA over 2, like that. So all this cost must satisfy RA plus RB plus RC equals 1. So the teleportation term ensures that every page receives some probability. So with teleportation now, so no page just goes to 0 like that. So because there's not the possibility of teleportation. So solving page rank by power iteration now, we do not necessarily need to calculate eigenvectors directly. So instead, we can repeatedly apply the page rank equation. So start with an initial probability distribution. So you have R of 0, that's at the initial stage. you have 1 over n all the way down. Then calculate R1 to be dmr0 plus 1 minus dv. So that's the power iteration now. So you keep iterating instead of just having to compute eigenvectors directly. Then R2 will be dmr1 that you got here plus 1 minus dv. And then if you continue, you have r raised per k plus 1 equals dmrk plus 1 minus dv. So eventually the vector converges to a stable distribution, which is of course analogous to when you ultimately compute the eigenvectors. So this method is called the power iteration method. Uh so this is an example of power iteration here. So the same matrix like before, and then we have the damping factor 0.85. That's the possibility, the probability of following a hyperlink. And then, of course, n is the length of the matrix itself. Then we have a uniform teleportation vector. V now is 1 divided by n. So we declare a matrix of 1. So because we're dealing with matrix all over n, then you have the initial page rank. That is R equals 1 over 1 over n. Then for iteration in range 100, so let's take, if you are now going 100 steps, so the new value of R is dm multiplied by R plus 1 minus dv from the formula we had before. So if the norm of new R minus R, is less than 10 raised per minus 10. So you can set this one and depending on whatever your desire is. So R then becomes the new R, and then it will break afterwards. Then you now output the final R, which is new R. So you print the page rank, you print the iterations, and you print the sum. So the page rank here, you have, at the end of the day, by the time you do all this, you see the page rank is 0.3877, 0.2148, 0.3973. And then so this takes place in 45 iterations. This condition is met in 45 iterations. And then the sum is 0.9998. So for you to understand what this is about, what if I make this raised to power 3, for instance, it means you will need less iterations. So in 13 iterations, we get there. So it means, so here, the more accurate you want the result to be, the smaller you make this particular condition. Okay. So 10 raised per minus 10 requires 45 iterations, while 10 raised per minus, was it 3 or 4? Required just 13 iterations. Then for the 3.16, using the matrix multiplication, the most important computational operation is the matrix multiplied by R. So this represents the redistribution of importance through the network. Mathematically, MR means take the current importance of every page and distribute that importance according to the hyperlink structure. Then D multiplied by MR represents importance transmitted through hyperlinks. So this is importance transmitted through hyperlinks, and 1 minus D multiplied by V represents importance introduced through teleportation. Therefore, the new value of R is the link contribution plus teleportation contribution. So both the hyperlinks and teleportation contributes to the ranking. So why does power iteration work? Suppose the matrix has eigenvectors x1, x2 up to xn with eigenvalues lambda1, lambda2 up to lambda n. An arbitrary vector can often be expressed as x equals c1, x1 plus c2, x2 plus c all the way to cn, xn. After multiplying by the matrix mx, we then have after multiplying by the matrix, right, we have mx, which is now c1 lambda 1 x1 all the way to c2 cn lambda sub n xn. After repeated multiplication, we can have the kth power of m now. So that also results to lambda 1 raised to power k all the way. So if one eigenvalue dominates in magnitude, its corresponding eigenvector eventually dominates the whole thing. Therefore, repeated matrix multiplication leads to dominant eigenvector. So this is the basic idea behind power iteration. We have such results in linear algebra too, if you check the playlist on linear algebra. So let's talk about PageRank as a random walk. There's another way to understand PageRank. Imagine a random surfer moving around the web. At each step, the surfer looks at the current web page, chooses an outgoing link, moves to the linked web page, occasionally teleports to another page. This creates a random walk on a directed graph. After many steps, the fraction of time spent on each web page approaches a stable distribution. So the stable distribution is the PageRank vector. Therefore, PageRank is equal to the long-run probability of visiting each page. So this is why PageRank can also be studied using Markov chains and probability theory. So one important link versus many weak links. Suppose page B receives one link from page A, then 10 links from low-ranked pages. So let's say the ranking of A is 0.8 and A has 4 outgoing links. So that means that A contributes 0.8 over 4, which is 0.2 to each of its link pages. Now, suppose 10 weak links each have R is 0.02 and each has only one outgoing link. All right. So you see that the importance of the link is it is important to have a strong link pointing at a page than to have many weak links pointing at it. So the combined contribution of these 10 links will just be 10 times 0.02, which is 0.2. Therefore, contribution from A alone is 0.2, whereas contribution from 10 weak pages just to it is 0.2 also. This illustrates the fundamental idea that the quality and importance of incoming links can matter more than simply counting the number of links. So, like I said, it is quality over quantity as far as PageRank is concerned. So the more quality pages point to your page, the better, the more important your page is. So implementing PageRank from scratch for import number as NP. So we define a function PageRank that takes the matrix, the damping factor, the tolerance limit, and the maximum iteration of 1000. So these are default values now. So compute PageRank using power iteration. So first of all, we have n, which gives us the shape of the matrix. That's the dimension of the matrix now. Then we have initial distribution. That's 1 over n, like we saw before. The uniform teleportation vector, that's also 1 over n. So for iteration in range of up to maximum iteration of 1000. So we now have the new ranking is damping multiplied by m times r plus 1 minus damping times v. So we check for the convergence. So this is the convergence line. So if the norm, that's the absolute value of the new r and the old r, is less than tolerance, then we return new r. And so we run this. Of course, we don't get any results here. Then we can go and test our function here. So the same matrix M the other time. So we then have this cost to be the page rank of M now. So page rank is already defined here. So we are calling the function page rank here. So we take the page rank of this M now. So we can change this M and get different values. So then we have pages A, B, and C. So for each of these pages now, we get the score in zip the pages with the score. So you want to pin the scores with the pages. So page A gets 0.387790. Page B gets 0.214811. Page C gets 0.39740. So that's like the 0.4, 0.2, 0.4 we had initially in this case. So this is us doing it from scratch instead of just going straight. Now, how do we handle dangling nodes? Dangling nodes are nodes without outgoing links, right? A dangling node is a web page with no outgoing link. So, for example, you have A, B, C, D. So A goes to B, B goes to C, and C goes to D. D, nothing goes out of D. So if D has no outgoing links, its column in the transition matrix would contain zeros. So this means probability could disappear from the system. This means probability could disappear from the system, yeah? So a common solution is to treat a dangling node as if it links equally to every page. So that's how we treat dangling nodes. So for n pages, then we replace its zero column with 1 over n, 1 over n all the way down. So this ensures that the probabilities will sum to 1 in that case. So Python dangling node fix now. So to fix Python dangling nodes, we share, we assume equal sharing to all pages available. So define a fix for the dangling nodes, taking M. So we replace zero sum columns with a uniform distribution. So we copy the M we used before, M equals M copy, and then the shape, we get the shape. And for J in range N, like in this range of the matrix now. So if N periods all close of MJ. So if you have any one where the sum is 0, then we now replace the every this all the rows there. So we replace every column with 1 over n. So in that case, we return M. So we define that. So let's now do a 5-page search network. Consider 5 pages A, B, C, D, E with hyperlinks A going to B and C. So it means B and C are sharing the ranking of A equally. Then B is giving C and D. So C and D are sharing the ranking of B equally. C is sending to A exclusively. So A takes everything from C. D is sending to C exclusively. So C takes everything coming from D. Then E is sharing to C and D like that. So the network contains different levels of connectivity. So our goal is to calculate a global importance score for every page based on these links now. So of course, based on the arrows alone, you can already see that you can see that RB. So if you focus on here, so for A, So we know A is taking everything from C. So RA is equal to RC straight up. Then RC, so you see RC here for this C now, C will be A RA over 2 plus RD. Because it is C is taken from both A and D. But since A is given to more than 2, so C is RA over 2 plus D plus RD straight up. Then for D now. So D is getting half attention from both B and E. So RD will be RB over 2, RE over 2, like that. And then interestingly, nobody is given to E. So E is like a dangling node. So the network contains different levels of connectivity. Our goal is to calculate a global importance score for every page. So what do we do? So we can construct the matrix this way. So import numpy as NP, and then we have the links. A is given BC, B is given CD, C is given A, D is given C, E is given CD. So the pages now, we can now list links dot keys now. Then N is length of all the pages. Then M is the NP. So we have 0 NN. So we have the initialization now. So for J in enumerate pages, so we have the outgoing is now the links of the pages now. So for targeting outgoing now, we have I pages.index. So this, instead of doing it manually, like I just described now, so you can then do it using a code like this. So for targeting outgoing, then you have I is pages.index target, then MIJ is 1 over length of outgoing. So then we print the pages and we also get the transition matrix. So I run this now. So once that is done, so that is run now. So we have the pages are A, B, C, D, E, first of all. And then you have, so like I said the other time, so we can form a matrix from here. So A is given to B and C equally. So we have, so from A here, so this is A, row A. So A, B, C. So okay, I mean we look at it according to the column. So A is given B and C equally. So we have half half. So we also see B is given C and D equally. So we have, so for B now, so we have A, B, C, D. So C and D equally. And then so C is given exclusively to A. That's why we have this C right here. Then D is given exclusively to C. All right, so that's what we have. So A, B, C, D. So this is C, then A, B, C. So we have this. Then E is given exclusively to is given equally to E and D, C and D. So this is A, B, C, D, E, then A, B, C, C, D. So you have 0 0.5, 0 0.5 each, like this. Then we calculate the 5 page page rank. So we have we fix the dangling nodes. So there's one dangling node, which is E, because E doesn't take, so for E, you see, nobody's given to E here. So E is not taking anything. So E is the dangling node here. So we fix the dangling nodes now by sharing everything equally. So whatever we now have these 5, we have 1 over 5 each, like that for E. So um, we calculate the we've calculated a fixed 5 page rank. So scores, page rank M, then ranking, we sort it, and then we print the page rank. And then when we do that, we see that so C, the page ranking for C is 0.353, for H is 0.330, B 0.1700510, D, we have these values like that. Then we can then visualize the ranking. So to visualize the ranking, clearly E is the least ranked because nobody is given to E, but I mean, we have because we have a fix for it, because we have described how to fix a dangling node here now. So we just give it, because we give it all through like that. So it also manages to get a rank. So we have all that. So visualizing the ranking now. So we need to visualize using matplotlib. So for the sorted pages, you have X naught for X in ranking, X1 for X in ranking, and then so we plot figure 8 by 5, and we now plot bar for sorted pages and sorted scores now. So matching. So we run this and we have the web page, the page rank, and the page score. So these are the web pages A, B, C, D, and E. So C is the highest ranked. and the page rank is around 0.35. A follows with maybe something like 0.34 or thereabouts, 0.33 or something. Then B is around 0.15 and D is like 0.10 and E is somewhere between 0.00 and 0.05. So let's talk about PageRank, not the entire Google search algorithm. PageRank is not the entire Google search algorithm. So PageRank is not the only thing for the Google search algorithm. So it is important to distinguish historical PageRank from modern search rank. So it would be incorrect to say Google search is simply PageRank. But PageRank is cool, but that's not all. So a better conceptual representation for search is retrieval plus ranking plus many signals. So modern search system can consider many types of information, including the query relevance, web page content, links, freshness, quality, location, structured information, spam signals, semantic relationships, and machine learning models. So because AI has come into things now, we don't have just mere page rank, we now have retrieval and many signals. So page rank is best understood as a historically important example of how graph mathematics and linear algebra can contribute to search ranking. So now, why was page ranking so revolutionary? Before PageRank, a simple approach to ranking could count how many pages link to a web page. So before PageRank, you just count, okay, how many important, how many pages link to a page? Not we don't even care about the importance, right? So PageRank introduced a much deeper idea that a link can be interpreted as a vote, but votes from important pages should count more. So weights are attached to the importance of the websites linking things up. So this creates recursive importance. So a page is important because important pages point to it. So that produces a mathematical feedback loop. So you have importance, then you have the links, and then you have importance and links. So it's more like a recursive stuff. So linear algebra provides a way to solve this feedback system, and that is the genius of the approach of page rank. So the deeper mathematical connection we see here as follows. The complete mathematical pipeline then becomes hyperlinks, meaning directed graphs, leading to the transition matrices, leading to Markov process, stationary distribution, and we get eigenvectors. And then for hyperlinks, you have web pages pointing to other pages. For directed graph, pages become nodes and hyperlinks become directed edges. So then transition matrix, the links determine probabilities of moving from one page to another. Markov process, the next state depends on the current state. Then stationary distribution. After many transitions, the probability distribution stabilizes. Eigenvector, the stable distribution satisfies MR equals R. Therefore, the stationary distribution is an eigenvector corresponding to eigenvalue 1 at the end of the day. So let's talk about PageRank and PCA, the eigenvector connection. So eigenvectors also appear in principal component analysis or PCA. So in PCA, eigenvectors are used to identify important directions of variation in data. In PageRank, an eigenvector represents a stable distribution of importance across a network. Both involve an equation of the form AX equals lambda X. But the matrices represent different things. For PCA, A is equal to covariance related matrix. For PageRank, A is equal to web transition matrix. So the mathematical tool is similar, but the interpretation is completely different. So for PCA, we have covariance related matrix, PageRank web transition matrix. So this is a powerful lesson in applied mathematics. The same mathematical structure can solve very different real world problems. Now, the question is why PageRank matters for AI. PageRank is an excellent example of applied AI mathematics because it combines several mathematical ideas like linear algebra, graph theory, probability, Markov chains, eigenvalues, eigenvectors, numerical methods, and iterative algorithms. So iterative algorithms, like we saw under power iteration, right? So the same mathematical ideas appear in many modern AI systems. So for search ranking, we have graphs and eigenvectors, recommendation systems, linear algebra, neural networks, matrix operations. For transformers, we have linear algebra and probability. For embeddings, we have vector spaces. For reinforcement learning, we have probability and optimization. For graph neural networks, we have graphs and matrix operations. For PCA, we have eigenvectors. For spectral clustering, we also get to use eigenvectors. So PageRank therefore provides an excellent bridge between classical mathematics and modern AI. So the most important equation that we've seen so far, as we begin to wrap things up. So if you remember only one equation from this lesson, remember the damped page rank equation, which is R equals DMR plus 1 minus DV. So this component corresponds with hyperlinking, and then this corresponds with teleportation. So for pages that have links, for pages that don't have links. So it says PageRank is equal to link-based importance plus teleportation importance. So the undamped version is R equals MR when there's no damping, when it is assumed that all pages have hyperlinks, which can be written as MR equals 1R. Comparing this with AX equals lambda X, it reveals the key idea that PageRank is an eigenvector problem. So PageRank is an eigenvector problem. The complete conceptual summary now. The web can be represented as a directed graph. Web pages are nodes. Hyperlinks are directed edges. A page distributes its importance through its outgoing links. Important pages pass more importance to the pages they reference. Then this creates a recursive ranking. The recursive system can be represented using a matrix. The stable ranking satisfies an eigenvector equation. Teleportation prevents the random suffer from becoming trapped. Power iteration can efficiently approximate the stable ranking. The resulting PageRank values provides a measure of structural importance. So the central transformation is from web to graph, from graph to matrix, from matrix to eigenvector, and from eigenvector to PageRank. So the big lesson is that mathematics can transform an apparently subjective question, such as which web page is important, into a precise computational problem. And that's the power of mathematics. So the final takeaway, PageRank demonstrates one of the most beautiful ideas in applied mathematics. A recursive real-world problem can become an eigenvector problem. So a web page is important because important web pages link to it, and the secular definition becomes that R is equal to MR, and then uh, which is an important, this is an important equation, which is an eigenvector equation, right? MR equals IR. With teleportation, we have R equals DMR plus IDVD. So this is the teleportation part. And computationally, we can repeatedly apply the matrix R K plus 1. This is the power iteration part now, DMR K plus 1 minus DV, until the ranking converges. So the remarkable journey is from hyperlinks to graph theory to probability to matrices to eigenvectors to PageRank. So this is the eigenvector trick behind Google search. So we have practice problems as usual. So, and I get to solve two of them as always. So here we have 20 practice problems. So here you can see 1 and 2. I'm solving 10 and 14. So you see 1 and 2 right here. 1 and 2. Then you can see 3 to 5, all clear here. 3 to 5. Then you can see 6 and 7. 6 and 7 can be seen here. Then 8, 8 and 9 are clear enough here. 8 and 9. Then problem 10 is a dangling node problem, so which we are going to deal with. I'm going to solve that soon. Then 11, 12, you can see 11, 12 here. Then 13 to, you can see 13 and 14. I'll be solving 13 also, which is see the effect of the damping factor. So how using the same network, calculate page rank for this ranking problem now. Compare the resulting rankings and all that. Explain how D changes the influence of hyperlinks versus teleportation. Then you see 15 and 16, 17 and 18, 19, then 20. 20 is really long, so we can see it in two parts. So this first part of 20 and the second part of 20. So let's go ahead and solve these problems as we bring this home. So we have a dangling node problem as we consider the four-page network. A goes to B, B goes to C, C goes to A, and D goes to nothing. So D becomes a dangling node. D goes nowhere. Okay, so here we see that the page ordering is A, B, C, D. like that. So for pages A, B, and C, each has an outgoing link. Each has an outgoing link. Therefore, A sends all its probabilities, all its probability, all its probability to B. So A to B, B to C, and C back to A. So A sends all its probability to B. 2. B sends all its probability, all its probability to C. Then C sends all its probability to A. C sends all its probability to A. So that's based on A to B, B to C, C to A, and D to nothing. So with that in place now, we see again that page D is a dangling node because it has no outgoing link. Page D is a dangling node because it has no outgoing links. It has no outgoing links. So that makes it a dangling node. So we then treat D. So we treat D as if it distributes. We treat D as if it distributes equally among all 4 pages. Among all 4 pages. Therefore, the transition matrix is this now. We have M. So let's do A, B, C, D, and A, B, C, D. So here now, of course, we know A. Okay, we come. This is how we come, right? So A doesn't have anything for A. A doesn't go to A. So, but A gives everything to B, then A gives nothing to C and nothing to D. Then B gives to C, right? B gives everything to C and every other thing is 0. Then C gives everything to A. So we have 1 here. C gives everything to A. So because D is a dangling node, we will assume, and then there are 4 items. So we'll assume that D shares equally to A, B, C, D and itself. It shares to A, B, C. It shares 1 over. It shares 1 to every equally among 4. So that's 1 over 4, 1 over 4, 1 over 4, and 1 over 4. So that gives us our transition matrix. So that's our transition matrix right there. So so this is more like you can see this as the source, and this is the source link. And this is the receiver link, if you like. Receiver page. Let me say source page. And then this is the source page and receiver page. So that's how it goes. So with that in place, now we have our transition matrix. So if you can check the column sums. So check column sums. Check column sums. So for column 1, right? If you sum up everything, we have 1. Sum everything, you have 1. Sum up everything, you have 1. Sum of everything here, you have 1 also. That's the way it goes. That's the way it should be actually. So if you sum up 1 over 4 in 4 places, that's 1. So you need to be sure if each column doesn't sum to 1, then something is wrong. So in that case, you can say therefore, every column sums to 1. Every column sums to 1. So this is important. This is important because the transition matrix, the transition matrix must preserve, total probability. So as a result of that, we can say that hence the modified matrix, is column stochastic. It is column stochastic. So the key idea is that a dangling web page should not cause probability to disappear from the PageRank system. So the key idea is that a dangling web page should not cause probability to disappear from the PageRank system. Okay, that's problem 10 right there. So let's take problem 14. So problem 14. So the damping factor, you know that the damping factor controls the balance. Damping factor controls the balance between following hyperlinks and teleporting to another page. So we can say that the PageRank equation is R equals dmr plus 1 minus dv. So if we consider four different damping factors, namely D is 0.50, 0.75, 0.85, and 0.95. So what impact do these have? So consider this now. So we see that for each value, so when D is 0.50, so we see that the suffer follows links with probability. The suffer follows links probability 0.50. Then, so the suffer follows links with probability 0.50 and teleports and teleports with probability 1 minus 0.50, which is 0.502. So there's a core probability of following a link or teleporting. Then, so in that case, right, the ranking is therefore The ranking is therefore strongly influenced by teleportation. So on the other hand, right, when D is 0.75, the suffer the suffer follows links with probability 0.75 and teleports with probability 0.25. So what does that tell us? Here we see that network structure. So network structure becomes more influential. So because the probability of following the network is higher, then when D is equal to 0.95, the suffer follows links with probability 0.95, probability 0.95, and teleports with probability 0.05. So the ranking becomes much more dependent on the network structure. So in fact, in the first case, the ranking is therefore strongly influenced by teleportation. Well, strongly influenced by teleportation for 0.5. Yeah, I mean, teleportation has like a fair share there. Yeah, so with this, we come to the end of all of that. So again, I'm going to show the questions and it will be over. Okay, you see question problems 1 to 3 all together here. 1 to 3, 4 to 6. Okay, I think I should just force that. So 4. So we have 4 and 5 there. 6, 6 and say 7. 6 and 7. 8 and 9. 10. 10 and 11. 12 and 13. 14. Okay, I think I solved 10, right? So these are 10 ideals. We're talking about a dangling node. So I also did 14, effect of the damping factor. So want to compare the resulting rankings, right? Okay, I didn't get to do all the ranking part, just did the impact, right? So explain how changing D influences the influence of hyperlinks versus teleportation. So we talked about all that. So you can see up to 16 here, and 17, 18, and 19, 19 and some part of 20, and the rest. Let me know how helpful this is for you, and there's something else you'd like me to try out. Feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you some special privileges that you will see when you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.